Okay, very good. Let's get started, even though it's ever fewer people, with every Tuesday getting fewer and fewer people. Okay, so now before we get started, I want to quickly recap the last lecture, and basically I want to do that by asking you questions. So last lecture you talked about non-deterministic Büchi automata. Can someone tell me what's the main difference between non-deterministic Büchi automata and non-deterministic finite automata? Yes?
They does work on infinite words instead of finite words. And
Exactly.
except if the accepting state is visited infinitely often.
Exactly. So they operate on infinite words instead of finite words. And on finite words, I mean, there is some point where you can stop in an accepting state, but on infinite words, there is no such thing as stopping somewhere, right? So we need to tweak the acceptance criterion, and the acceptance criterion is defined in a way that says a run for a word is accepting if it visits accepting states infinitely often. Now, who of you has seen omega automata, Büchi automata in other lectures? 1, 2, 3. Okay, not too many. So for you, probably, these two lectures are rather boring, maybe, because it's the standard contents. But it's good that other people here don't know all the contents already. Now, last lecture, you have shown that omega regular expressions correspond to omega regular languages, right? This is what Professor Khatun proved to you. And in this lecture now, we're going to take a look at the closure properties of omega regular languages. What does that mean? Well, on languages of finite words, namely regular languages, you all know that they are closed under union, intersection, and complementation. What does that mean? You take any two regular languages and you build their union, still a regular language. You build their intersection, still a regular language. And you take one and complement it, and you will still get a regular language. And here, in the case of finite words, you also have concatenation and Kleene star, meaning that if you concatenate two languages or you iterate them finitely often after another, then you will still get a regular language. So they are, in some sense, pretty much closed under the common operations. And now in this lecture we will see that omega regular languages, for omega regular languages you have a very similar thing. They are also closed under union, intersection, and complementation. Now, why are concatenation and Kleene star missing maybe here? Yes?
Because they are already infinite words.
Exactly. They don't make sense to begin with, right? If you have finite words, then you can put one finite word after the other. But if you have infinite words, how do you put one infinite word after the end of another infinite word? There is no such thing as an end of the first word to begin with. Okay, so the interesting properties for infinite words for omega regular language are union, intersection, and complementation, and as it turns out, omega regular languages are closed under all these operations. And we're not going to show all of them, but I'm going to illustrate let's say two of them. So do you have a hypothesis how you can prove that it's closed under union? So take two omega regular languages, take the union of them. Why is it still an omega regular language? Maybe you have already proved that. Think of the contents of the lecture, of last lecture. You proved that in omega regular expressions, you have a plus operator. Well, what does the plus operator do? It means take the language of the left thing, join it with the language of the right thing. And this is exactly the union of two languages, right? So you already have this. So union, you already proved last lecture, in fact. In this lecture, we're going to show that it's also closed under intersection, but we're going to need a few tools left and right for that. But this I will show to you. And the complement, we're not going to do it. Those of you who have seen omega automata in other languages, they probably know that. And I will show you maybe some clues here and there why this is the case. It's really non-trivial to complement an omega regular language. So in a finite case, what would you do? I mean, you have an omega regular language, so you have an automaton for it. You maybe need to determinize it, and then you complement the accepting states, and then you have an automaton for the complement of the language you started with. Not as easy for omega regular automata. Okay, but the main content of this lecture is going to be the intersection, and as I said, there's going to be a few tools here and there that we need in order to do this. So let's start with non-emptiness for non-deterministic Büchi automata. You're also going to need this in the follow-up lectures and algorithms. So the question is, given a non-deterministic Büchi automaton, set of states, alphabet, transition function, initial states, accepting states, the question is there some word that is accepted by the automaton? Well, and in order to decide this, we're going to prove the following theorem that says if we have such a non-deterministic Büchi automaton, the language of that automaton is empty if and only if this huge thing here holds. Well, this is very long, but it's rather easy to understand. It means there exists an initial state and a finite state, a word x that is potentially empty, just a regular finite word that can be empty, and a non-empty finite word y, such that we can go from q0 to p by reading x, and we can go from p to p via y. Well, if you draw this, what does it mean? It means you start in some initial state q0, you read a possibly empty word x, you get to some final state or some accepting state p, and from p you can read y and reach p itself. And then I hope you intuitively already see that you would kind of accept the word x, y to the omega, right? Because we're starting in the initial state and visiting some accepting state infinitely often. Okay, let's prove this theorem up there. Let's start with the direction from left to right. Now for this, we can assume that the language that the automaton accepts is not the empty set. Okay, what does that mean? That means we can take a word sigma, a0, a1, and so on, that is in the language, really just some word. Good. Now, because this word is in the language, it means there needs to be an accepting run. So we let pi, q0, q1, and so on be an accepting run of the automaton for the word sigma. So far, so good. Now, because this run is accepting, we know that it needs to visit an accepting state infinitely often, some accepting state infinitely often. So let's write that down. So we take some accepting state p, such that this one accepting state that we chose appears infinitely often in the run pi that we chose. Such that qi, so the position, so the run pi at position I is exactly this accepting state for infinitely many I. Now, why does it have to exist? I mean, you could ask, why do we see any particular one accepting state infinitely often? Well, because we only have finitely many accepting states, right? We need to visit the accepting states infinitely often, but there are only finitely many of them, so it cannot be the case that we visit a different one every time. So we must see one of them infinitely many times. Okay, now we can choose I and j, two positions in the word that are distinct, such that qj is p. So at both positions, I and j, in this accepting run, we see the accepting state p. Now, what does our run pi that we chose now look like? It looks like this. Q0, Q1, Q2, dot, 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 up until Qi, and then at some later position, Qj, and then it goes on, right? I mean, this is what we started with. This is the run pi on sigma. Now we said we have two positions, I and j, that are distinct where the automaton is in the accepting state p. This means this is p in f, and here in this state is also p in f. Okay? But now we know that the automaton from Q0 up until Qi, it reads the word A0 dot 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 until AI minus 1, right? This is the word we started with, A0, A1, and so on. And up until Qi, we read the finite prefix A0 to AI minus 1. And let's call this one X. And similarly, here from Qi to Qj, because the positions were distinct, we read a non-empty word AI dot 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 aj minus 1. And this word we're going to call y.
You're out of the writing bounds.
Sorry? Oh, sorry. Sorry. Can also, is this large enough? Can I zoom out, or do you rather want me to push it up? Is that still readable? Okay. Because it's good to have the whole picture, hopefully, on one slide. Okay. But now, given that we define the words x and y to be like this, what does it mean? It means that we can go from Q0 by reading x, right? We go to Qi, which is p. So p is in delta of Q0 and x. And at the same time, we also can go from p, from this Qi, by reading y, go to Qj, which is also p. So we get p in delta of p and y. And you see, this is exactly the condition we had over there, meaning that from the initial state, we can go to some accepting state p via reading x, and from there on, we can loop with a non-empty word y. Okay, is this clear? Very good. So I would now move to the other direction. Let's do that. Okay, now for the sake of clarity, let's write down the whole right thing again, just to make sure that we have our assumptions. So we take Q0 in the initial states. We have an accepting state P and F. We have a possibly empty finite word X. We have a non-empty word Y, such that we can go from, P in delta of Q0 and X. We can go via X from Q0 to P. And we have P in delta of P and Y. This is just the condition. Okay, but then let's look at the word X, Y to the omega. Let's call it sigma. And now it must have a run of the form Q0 dot 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 up until P, right? Because this condition says by reading X, we can go to P from Q0. So by reading X, we can make that move. And then from P, we can go to P by reading Y. and we can repeat that. And so on. Okay, so we have constructed a run for the word sigma, and now all we need to do is to check, is it accepting or not? And as you can already see, it is accepting because we visit an accepting state infinitely many times, namely p. So we visit p infinitely often, and and since we have that p is accepting, this whole run is accepting. And therefore, we clearly have that the word xy to the omega is in the language recognized by the automaton A. And in particular, we have L omega of the automaton is not empty. Okay, I hope this is also intuitively clear. But this whole proof and also this thing, it gives you even more. It gives you that if the language of the automaton is non-empty, then there are very special words that we recognize. Special in the sense that they have this form, some finite prefix x, and then repeating the same word over and over and over again. This is what is called, it's not ultimatively periodic words, ultimately periodic words it's called. And I mean, this is also a very interesting property. So when the language of the automaton is non-empty, you don't have to look for, if you want to check whether this is the case, you don't have to look for very special words. It suffices to look for very special words, namely ultimately periodic words. Okay? Okay, and now this theorem, it directly gives you an algorithmic way to check whether the language accepted by a non-deterministic Büchi automaton is empty. Well, why? Well, because you can essentially do some graph search, say a depth first search, from the initial state, from the initial states, if there are some, to find some accepting state that is basically on a cycle, right? That looks like this picture. So by graph searches, you can decide the emptiness problem for non-deterministic Büchi automata in polynomial time. Good. Now, in the finite word case, you all know deterministic finite automata, right? So let's look at deterministic Büchi automata. Well, very straightforward. What are there? What are they? A non-deterministic Büchi automaton is called a deterministic Büchi automaton if there is a unique initial state. So we mustn't have the opportunity to start at different initial states. So the initial state set is basically a singleton. And no matter which state Q you are in, and no matter which symbol you use, you read, the successor set, the set of states that you can reach in one step with this character, is at most one element large. Right? This is intuitively what you also have for DFA. So if you read a symbol from some state, there's only one unique successor state at most that you can go to. And now if Q0 is the singleton set just containing one initial state, lowercase q0, then we just write lowercase q0 for DBA to express that there is exactly one. Okay, and here's an example. I mean, this is a deterministic Büchi automaton because it has just one initial state, namely q0. The other state is not initial. And if I look at the alphabet consisting of A and B, and if I look at the outgoing transitions of q0, for example, if I choose B, then there is one unique successor, namely q1. If I look at the character A, there is one unique successor, namely q0. And the same thing holds for q1. So it's a deterministic Büchi automaton. And we can already see that it accepts the language infinitely often B. Well, why? Because, I mean, the acceptance condition is still the same. It says you need to visit Q1 infinitely often. But how can we get to Q1? Well, we need to read a B. We are allowed to read some A's in between, that's perfectly fine, but once in a while we always have to go to Q1 in order to be accepting, right? And if you do this, you automatically have infinitely many B's in your word. Is that clear? Very good. Now for a non-deterministic finite automata, you know that I can take an NFA, recognizing some regular language, and I can use the power set construction to determinize it, right? I can get, by an algorithmic construction, I can get a very easy algorithmic construction. I get a deterministic finite automaton that recognizes exactly the same language. Well, the obvious question is, for non-deterministic Büchi automata, can we take our NBA and then make some power set construction and then go to a DBA? And this is what we're going to look at now. So this is an NBA for the language eventually forever A. Why? Because initially we start here, we can read an arbitrary prefix, but at some point, in order to be accepting, we need to make this switch to the accepting state, and then you can only cycle with A's. So from some point on, you will only read A's in order to be accepting. Okay, let's make this more complete in a sense. So as soon as you have decided non-deterministically in this case to go to the accepting state, if you read a not A at some point, you can reject the word. That doesn't change the language because you can still non-deterministically guess the point from which on A holds forever. Okay, let's do the power set construction that you hopefully still vaguely recall from lectures on automata theory. And then the resulting thing would look like this. So let's maybe look at some transitions, why they are there. So starting in Q0, there are two cases. I can read either not A or I can read A. If I read not A, well then the only state that I can get to is Q0 again, so I have a not A loop on Q0 in the power set automaton as well. But if I read an A from Q0, there is a non-deterministic choice, right? There are two possible successors. I can either stay in Q0 or I can move to QF. And this is reflected in the construction by moving from the state Q0 via an A to like the meta state that says, well, I don't know, you are either in Q0 or you can be in either Q0 or QF, right? This is the usual thing that you do for NFA to DFA constructions. And then you can continue that process, and then you will get this automaton in the end. This is just some examples. And as it turns out, this deterministic Büchi automaton accepts the language infinitely often A. Well, that's too bad, right? Because we started with eventually forever A, and what we get is infinitely often A. I mean, you can have a look into the automaton. So in order to be accepting, you either need to visit this state infinitely often, so you can read some not A's, then an A, and then A forever. That is fine, but that doesn't allow that you have, for example, not A, not A, not A, then an A, then again not A, not A, not A, and so on. So you might also want to, so you also need to consider the last part in order to completely characterize the language. And this part back here, for example, you would accept the word A, not A, and then A, not A, A, not A, A, not A, A, not A, because this is an accepting state. You visit it infinitely often. But the word you have accepted is still A, not A, and then alternating in an alternating way A and not A, which is definitely not satisfying eventually forever A. Right? Okay, so what have we now seen? We have seen that the usual power set construction from NFA to DFA, if we apply it like this to NBAs, doesn't work. It just fails. It gives you a different language. It may still be interesting in some sense, but it's not language preserving as you would have in the finite word case. Okay, let's look at the complementation of deterministic Büchi automata. We will come back to the language equivalence thing for DBA in a minute. Oh, sorry. Okay, you all know that you can complement a DFA. The D is important, right? It needs to be deterministic by just complementing its acceptance set, right? You take the DFA and you basically drop all the accepting states and make all other states accepting, then you get exactly the inverse, the complement of the language you accepted with your original automaton. A natural question now is, does this hold for deterministic Büchi automata? And let's look at this example. This is a DBA for the language infinitely often not A, right? Because we need to see this state infinitely often, and we can only go there via not A. So it's, I hope it's clear that it's infinitely often not A, the language that is recognized with this automaton. And yeah, let's just invert the acceptance set, right? Just like we did for DFA, and then we get this automaton. And yeah, what's the language that this automaton accepts? Yes?
It would also accept infinitely often not A.
I would say infinitely often A, right? Right? Because basically you can only get to this state via reading an A, but I think you meant the right thing. Okay, so it accepts the language infinitely often A. Now I hope you see this is not the complement of one another. It might be tempting to think that it is because you're saying, yeah, not A, and so I you know, complemented the A back here, so it should be fine. No, it's not. Because the complement of infinitely often not A is only finitely often not A. Okay, that's something else than infinitely often A. In particular, so if you reformulate infinitely often not A, the complement is from some point on always A, which is not just infinitely often A. So what do we learn from this? If we take a DBA, even though it's deterministic, and we reverse or flip the set of accepting states, you will get a different language. You will not get the complement. Okay, so on the previous slide, you've seen if we take an NFA, an NBA, and we determinize it using the power set construction, it doesn't give you an equivalent DBA. Well, you could say, yeah, let's do something else. Let's do a different construction. I mean, we're not bound to the power set construction of finite automata. So, you know, let's just do something else. As it turns out, you know, there is no hope to do that. Because, as we will prove in a minute, there is no DBA for certain omega regular languages. Omega regular languages are strictly more expressive than deterministic Büchi automata. So by picking or by going for determinism in the automaton, you lose expressiveness. In the finite word case, this is not the case, but for omega automata, this is the case. Now we're going to prove there is no deterministic Büchi automaton that recognizes the linear time property eventually forever A, from some point on forever A. Okay, and the theorem for this is saying that there is no deterministic Büchi automaton over the alphabet AB, such that the language recognized by this DBA is exactly the language characterized by this omega regular expression, saying I can read an arbitrary prefix of A's and B's, but at some point I need to decide from now on only A's. And you know, if you instantiate this, this theorem up here, by choosing A to be the set containing A and B to be the empty set, you get the result that we had before, because this A, technically it's an atomic proposition. It's not a character of, that is read by the automaton, right? But this theorem gives you the result that there is no DBA for the linear time property eventually forever A. Okay, let's prove that. Proof. Okay, so you know, a straightforward direction that we are going to follow is we assume that there is a DBA that does exactly what is stated here, that it's not possible. And then I'm going to show you it cannot be the right DBA that you started with. Okay. Assume you have that that the language that we're going to call L from now on, for simplicity, it's exactly the language that we have on the slides. A or B for finitely many steps, and then from some point only A. Let's call that one L. Now assume that this is recognized by some DBA that we call A. Now the DBA consists of Q, sigma, delta, Q0, and accepting states F. Okay, so we assume the contrary, and now we're going to show, well, cannot be the case, cannot be the right DBA. Okay, let's look at some word, call it sigma 1. And it's the word we pick a to the omega. Now is a to the omega in our language or not? In L. I mean, this is L, right? So you can start with an arbitrary prefix of A's and B's, and at some point on you only see A's. Is a to the omega in this set or not? I see some slightly nodding heads. I hope we all agree it's in the language, okay? Okay, so we pick the word that is in the language. What does that mean? Because our assumption is our DBA recognizes this language. It means that we must have an accepting run, right? Okay, so we have this word in the language. Then there exists a natural number n1 greater or equal than 0. Such that we have that from delta, that from Q0, if we read exactly n1 A's, then we are exactly in the state Q1, and the state Q1 is an accepting state. Well, why is that? We have a deterministic automaton, remember? So, and first of all, because the word is in the language, we know there must be an accepting run. And we know that this accepting run, at some point, it needs to visit an accepting state infinitely often. So in particular, after some finite number of steps, we need to visit one, call it n1. And because we know it's deterministic, there can only be one state that we're in after any number of steps on a particular word. Okay, so this is a singleton as A is deterministic. Okay, so far so good. We looked at one word and we said that after n1 A's, our automaton must visit an accepting state. Let's look at another word. Call it sigma 2. And how do we construct sigma 2? Well, we take n1 A's, then we sneak in a B, and from there on, we read A forever. Now, is this word in our language? It is. So this one is in L. But now we can repeat this, right? The argument can say, well, then there exists an n2 strictly after n1, such that if we read from Q0, from the one initial state, an1, B, and then an2. Also, sorry, this should be an equal sign because this is exactly the set consisting of one state. Now, if we read this prefix, again, we must be in some accepting state, call it Q2. Following the same argument as above. Again, it's just one accepting state that we can be in after having read this finite prefix. Okay, let's do this one more time. So let's take a word sigma 3. It's straightforwardly defined by having n1 A's, then a B, then n2 a's. Again, we're sneaking in a b, and going to repeat a infinitely often. Again, is in our language, because eventually forever a holds. Again, there exists now an index a3 greater than n2, such that if we read the prefix q0, an1, b, an2, b, an3, we are in some accepting state q3. Now I hope you see where this is going, right? We can continue this process on and on and on. So where do we get? So continuing this process. Well, what does it give us? It yields a sequence, actually two sequences, but the one is of natural numbers, n1, n2, and so on. And in particular, we also get a sequence of accepting states, namely q1, q2, q3, and so on. Such that the following holds. You know, essentially summarizing the process above. So we have that delta starting from q0. If we read the word an1, b, an2, b, an3, and so on, up until an I minus 1, b, a, ni. So this is basically the construction for this arbitrary ni. We are in the accepting state qi. Okay, where can we go from here? Well, we know q is finite, right? And in particular also f then. Well, what does it mean? It means because we have a sequence of finite prefixes that all end in an accepting state, in exactly one accepting state. It means that we have at least two positions where we have to be in the same accepting state, because there are only finitely many, right? Infinitely often, we are in some accepting state, so because we are only finitely many, we need to be in one of them infinitely often. Well, in particular, that means that we have two positions in the word I and j that are distinct. Or not two positions in the word, but rather two positions in these sequences of natural numbers and states. Such that we have delta q0, reading from q0 the prefix n1, b, or a n1 times, then a b, and so on, b n I times an a, is the same accepting state as reading the different word that goes until nj. So q a n1, b dot dot dot, b a n I, right? So this is up until now it's this word, but we're going to put something behind that up until b and then a n j. Right? This is just formally saying that because infinitely often we visit an accepting state, at least I must visit one accepting state infinitely often, and in particular I need to visit it twice. Right? Meaning I can pick two positions in our sequences such that the set, this accepting state that I reach after this word is the same as the one that I reach after reading the extended word. But what does this mean? It means that our automaton, our DBA that we started with, has an accepting run on the word A n 1 times, B A n 2 times, and so on. So this word up here, B A n I. And from there, we're going to repeat the missing fragment from this finite prefix to that finite prefix. We can iterate that infinitely often because we just said we were in the same state after reading these two words. It means that we can go to this accepting state and then loop this extension of the word infinitely often. So what does this extension look like? It's B A N I plus 1 times B A N J. It's exactly the part of the word that we appended here and got to the same state. But, okay, why does this now contradict our assumption? Well, we have a word that is accepted by our DBA, but it's clearly not in the language because you have B infinitely often. Right? So this is not in L, and let's write it down, which contradicts that the language recognized by our DBA is the language L we started with. Okay, so we assumed we have a DBA for the language, and then we showed, well, it's not the language, right? So it breaks. Okay, let's move on. Well, this is somewhat, it's bad news because it means it's not easy to get a deterministic automaton, and sometimes it's not even possible to get a deterministic automaton for the same language, deterministic Büchi automaton. And I already stated this. If you look at the languages that you can recognize via some deterministic Büchi automaton, this is a proper subclass of the omega regular languages. It's not only a subclass, but it's really a proper subclass. There are languages, omega regular languages, that are not DBA recognizable. And we've seen on the previous slide, it's also not closed under complementation, right? I mean, we directly get this because we had the DBA for infinitely many B's. But if you would complement this, you will get the language only finitely many B's, and we just saw that this is not DBA recognizable. We just proved, I mean, not with the B's, but for a very similar language, we proved it's not DBA recognizable. And for this one, we have a DBA. For this one, you can prove there is none. It means DBAs cannot be closed under complementation, and the DBA recognizable languages cannot be closed under complementation. Okay, let's finally come back to our main goal of today, the intersection of omega regular languages, showing that it's closed under complementation. And for this, we're going to need a tool that's called the generalized non-deterministic Büchi automaton, that we will also use in future lectures a bit. And so how does it generalize a non-deterministic Büchi automaton? Well, it's almost the same apart from the acceptance condition, right? So you also have states, alphabet, transition function doesn't change, set of initial states doesn't change. The only thing that instead of like a regular f, we now have a curly f. Well, why do we have that? It means we have, instead of having one set of accepting states, it means we have a set of sets of accepting states, right? So instead of just saying, yeah, Q0 and Q1, either one of them needs to be visited infinitely often, we can now require more. Why is that? Because we now say a run is accepting on some infinite word sigma, a run Q0, Q1, Q2, is accepting if it visits all the sets that are in this curly f infinitely often, right? So instead of saying, yeah, here's this one set, and you need to visit it infinitely often, I'm going to give you a set of sets, and in order to be accepting, you need to visit all of them infinitely often. You can choose which state in the individual set, that's up to you, but you need to visit all of them infinitely often. And if you write that down formally, it's like this. So for every regular f, so for every set of accepting states in our new acceptance condition that is a set of sets, we need to have infinitely many positions in the word such that the state qi is in this f. Okay, that's important. So generalized non-deterministic Büchi automata, everything is the same as non-deterministic Büchi automata, but we have sets of accepting states, and in order to be accepting, we need to visit all of them infinitely often. Okay, very straightforward. What's the language accepted by GNBA? Well, it's the set of words that has an accepting run. It's the same as before, we just changed the acceptance condition. Let's look at an example GNBA over the set of atomic propositions, so crit 1 and crit 2. So it's a GNBA taken from the mutual exclusion world, and it looks like this. So if one initial state Q0 and two accepting states Q1 and Q2, but they are, in different classes. Okay? So here we have a curly F saying you need to visit Q1 infinitely often, and you need to visit Q2 infinitely often. Okay? That's a difference to putting them into one set. Why is that different? Now, let's assume for the moment that we look at this as a regular NBA, and we say both of them are accepting. Well, then, for example, the word Q0, Q1, or the run Q0, Q1, and so on, it would be accepting because it visits an accepting state infinitely often. But in a GNBA, if we use this acceptance set, it's not accepting anymore because it requires both of them to be visited infinitely often. And if you look at this GNBA, you see that you need to visit both of them infinitely often, meaning you have to see crit 1 and crit 2 infinitely often. Is that clear? Good. And therefore, we can specify the linear time property, for example, using this automaton that says infinitely often crit 1 and infinitely often crit 2. If we look at regular NBAs and just have one accepting state, then this automaton would recognize a different language. Okay, here's the reasoning on the slides, but I hope you intuitively see that it recognizes infinitely often crit 1 and infinitely often crit 2. Let's look at this generalized non-deterministic Büchi automaton. One initial state, you can read an A here. And with this acceptance condition, what language does the GNBA recognize? Nothing, right? Because the condition says you need to visit Q1 and Q2 infinitely often. Well, show me a run that visits both of them infinitely often. It's not possible because as soon as you have visited Q2, there is no way to see Q1 again. So language is empty. Let's look at a different GNBA with two sets of accepting states, namely Q1 and Q3. So the boxes are forming one set of accepting states, and Q2 and Q4 are forming one set of accepting states. And as you can probably see, what would you say is the accepted language by this automaton, for example, described as an omega regular expression? Yeah, I mean, you start with an A, and then you can see B infinitely often. So you could decide to cycle just here. So you get this part of the omega regular expression. And the other part is you start with an A, and then you read an arbitrary number of B's, go there, read an A again, and then cycle between A and B forever. Okay? But because these cycles, they are accepting because they contain accepting states from both of these sets. That's the important part. Okay, because that confuses people quite a bit, let's talk about what happens if the acceptance condition is empty for Büchi automata. Now let's look at the same automaton once as an NBA and once as a GNBA. Suppose the NBA has no accepting states. What's the language that it recognizes? It's a stupid question, I know, but just, yes? It's empty, exactly, right? Because you see, the definition says you need to see an accepting state infinitely often, but there is none, right? So it's empty. GNBA. Let's suppose we have no set of accepting states. What's the language recognized by the automaton?
Infinitely often 8, I guess, because we still, I mean, there is no set we have to visit, so we always visit every set.
Exactly. So the language is in this case, the language a to the omega, exactly one word. Well, why is that? Because it suffices to have one infinite run for a word. Because remember, the definition said for all of the sets that are in here, you need to, satisfy being infinitely often in that set. But as there are none, for all quantification, it's directly fulfilled. And and it's the word a to the omega because we still require an infinite run, right? So if there is no run, then you can also not accept the word even if you don't have to check for the acceptance criterion with respect to the accepting states. Okay. Now, suppose we have a GNBA with an empty acceptance condition. So no set of accepting states. It just happens to be like that. Do you think there is always a GNBA that has a non-empty set of accepting states that recognizes the same language? Yes?
I'd say you can just choose the set of all states.
Exactly, right? So it's a very trivial transformation. Instead of taking none, you just say, well, all of them are accepting. And that's perfectly fine. Exactly. Good. So we can now, for example, always assume that our GNBA has at least one set of accepting states, right? Because we can also always do that transformation. And now we're going to look at the transformation from generalized non-deterministic Büchi automata to non-deterministic Büchi automata. And the claim is, I give you a GNBA, possibly many sets of accepting states, and you can construct an NBA with just one set of accepting states that recognize the same language. What does it mean? It means non-deterministic Büchi automata and generalized non-deterministic Büchi automata, same expressivity. Okay? Omega regular languages, same thing. And I'm not going to prove that formally, but I'm showing you basically the intuition of the construction. Now suppose we have a GNBA G. I mean, this is what we start with, and we want to construct an NBA A from that. And our GNBA has accepting sets F1 up until Fk. Now, one thing is, I just said that we can assume there is at least one in there, right? Otherwise, we can construct one that is equivalent that has one accepting set in here. Now, for the case where it's one, it's actually pretty boring because then we already have an NBA. Because we require you need to visit that one set infinitely often where you can then directly take that set as the acceptance condition for your non-deterministic Büchi automaton. So let's assume we have at least two sets of accepting states in our generalized non-deterministic Büchi automaton. And the intuition is now that we create k copies of our GNBA. And this looks as follows. So we take the GNBA, it's basically like a blueprint, and then we put k copies, one for each accepting set next to one another, right? Don't forget about the arrows right now, but we have one copy, second copy, and so on until we have a copy for the last one. We start in the first copy. This is where our initial states are. We just start there. Okay, but we need to decide, okay, where do we put the transitions? And now the idea is to say, in the first component, in the first copy of our GNBA, we basically divert all the transitions going out of the accepting states of F1 into the second copy. All other transitions remain in this copy, but as soon as we have seen some state that is accepting with respect to F1, we move to the second copy. And we do the same here, and so on. So what you get is essentially you're always switching the copy one step further once you have seen an initial state that belongs to this copy. So here you need to see an accepting state from F2 in order to change to the next copy, and so on. And from the last copy, obviously you don't move forward, but you go back to the first one. So it's to be understood modulo the number of acceptance sets. Okay? And now I hope that you already maybe intuitively see that by this transformation, now if we make only the states of F1 accepting in the first copy, we drop all the other acceptance conditions with respect to F2 and Fk, but we only require the states of F1 in the first copy to be visited infinitely often. Well, first of all, what we get is an NBA, right? Because we have only one set of accepting states. Now, obviously, you can ask the question, why does it recognize the same language? I mean, we went from k sets of accepting states to just one. Well, but I hope that you intuitively see that by moving through the copies and only allowing to switch the copy once we have visited the corresponding acceptance set of this copy, it means that if you have an accepting run in your GNBA, it needs to visit F1, F2, and Fk, and so on infinitely often, but then it can also go through this cycle infinitely often, and in particular visit the accepting states in F1 infinitely often. So it will also be accepting in this construction. Okay, so by creating copies of the GNBA, we have got rid of all the acceptance sets, but it remains only to have one. Yes?
How does this construction deal if F is empty?
Yeah, I mean, as I said, we assume that it's not empty because we can always add something. If it has size 1, then we have an NBA. So our assumption is it has at least 2. Yes. But otherwise, good question. This is why we put it on the slides that you can always come up with an acceptance condition that is non-empty and recognizes the same thing. Okay, so we're not going to prove that this works, but I hope you intuitively see that because we're talking about infinite runs, this construction gives you the same set of accepted words, but now recognized by a non-deterministic Büchi automaton, not a generalized non-deterministic Büchi automaton. But of course, it comes at a price. So you started with a GNBA of size something, size n. Then the size of the NBA, it will be the n, the size of the GNBA, times the number of copies we needed, namely number of acceptance sets in our acceptance condition. Okay, let's look at an example. Let's take this GNBA G. I mean, you know it from the previous slides. It says infinitely often crit 1 and infinitely often crit 2. These are the words that it recognizes. And this is the NBA you get when you construct it, as I've shown you before. So this is the first copy. These are the states where you have 1 in the second component. It means this is our first copy. This is our second copy, the states where we have a 2 in the second component. We start in the first component in the initial state. So in this compound state, Q0 and 1. And then we look at what transitions should there be now in our NBA. Since Q0 is not an accepting state in F1, right? We maintain all its transitions and stay in the first copy, which is why you see that we can basically mimic the behavior of Q0 here, but remain in the first copy. Here, now something changes, because Q1 is in the set F1, in the first set of accepting states, meaning that we change its transitions in a way that they move to the second component. Here, the other accepting state, Q2, it's in the second acceptance set, F2. We're keeping the transitions in the first copy. We will only change something in the second copy, right? Every copy is associated with one set of accepting states. And then you continue this process, and here you see the symmetrical case where we, using the transitions from Q1, which was in F1, we stay in the second copy. But if we visit the state Q2, which was in the accepting set F2, we move to the first copy again. And you already see that in order to be accepting here, you need to visit this one, because Q1 was from F1 infinitely often. But in order to do so, we also need to always go through Q2, which was an accepting state in F2. Right? Okay. So long story short, generalized non-deterministic Büchi automata, not more expressive than non-deterministic Büchi automata. Same thing. We can use this construction to reduce it, but it's still sometimes handy to have it. Why is it handy? Well, I'm going to show you now that the product construction for the intersection, the product construction that we need is going to use GNBAs, because that will come in handy. Okay, so last part of today, we're given two NBAs, A1 and A2, defined as usual. And now our goal is, how can we define an NBA A such that the language of this non-deterministic Büchi automaton is the intersection of the language of the two automata A1 and A2. And I hope you also, again, vaguely remember from courses on automata theory that if you want to do the very same thing on non-deterministic finite automata, what you do is you essentially let the automata run in parallel. So they need to take all the steps synchronously, and you accept a word if both of them, or I shouldn't say it, you make a state accepting in this product construction if both components of the automata are in accepting states. Because what does it mean? It means that if you have a run and the automata move in parallel and you come to an accepting state, then both of the automata accept this word, meaning that it's in the intersection, right? Okay, so this was the product construction for NFA, vague reminder. And now we're going to do essentially the same thing just on NBA. And what do we do that? How do we do that? We also let A1 and A2, the two NBA, move in parallel. And we need to check that both of them are accepting, right? As was the case for non-deterministic finite automata. But as it turns out, it's not enough now to just say, well, let's make the states accepting in which both components are accepting. No, this will not work. But we will need to tweak the acceptance condition a bit. And we will have to formulate that in a way that says both F1, so the acceptance set of this one, and the acceptance set of the second one are both visited infinitely often. And as you can see in this condition, it directly gives you a GNBA, right? We're going to look at details now, but it tells you if you do the product construction on GNBA, on NBA, you will get a GNBA because you have two sets of accepting states in the end. Okay, so how do we define the product? Now, the state space, just as for NFA, it's the Cartesian product of the state spaces of the two involved non-deterministic Büchi automata, A1 and A2. The alphabet stays the same. The initial states are the Cartesian product of the initial states of the two involved automata. And now we come to the interesting part, which I already alluded to. The acceptance condition now has two elements. So it's a GNBA. And the acceptance condition says, along a run, you must visit states who are in an accepting state in their first component with respect to the first automaton infinitely often, and you need to visit states that are in an accepting state in its second component with respect to the automaton A2 also infinitely often. Both of this has to hold. Okay? So you have two set of accepting states that need to be visited infinitely often. And the transition relation is defined just as it was for NFA, for the product construction on NFA. It means if you are in a compound state Q1, Q2, and you read an A, well, where do we go? Where can we go from there? We can go to all states P1, P2, such that I can go in the automaton A1. So via delta 1, I can go from the first component Q1 via A to this P1. And in the second component, I need to make a step from Q2 via A to P2. Right? This is the same thing as we had for NFA. So the only thing that really changed in this construction in comparison to the finite word case is this acceptance condition. But I've already shown you, I mean, this is not a big problem, right? We constructed a generalized non-deterministic Büchi automaton, but we can always get rid of the additional accepting sets and reduce it to a non-deterministic Büchi automaton again. So what have we done then? We have taken two NBA, constructed a GNBA that can be reduced to an NBA again that recognizes the intersection of the languages accepted by the two input automata. Let's look at a boring but still an example. Okay, we have A1 that looks as follows. Consists of two states, Q1, which is an accepting state, and we have Q2 here. And both of them are labeled with an A. And let's look at a very similar automaton A2. It has two states, R1 and R2. And in this case, R2 is accepting. Yet both transitions are also labeled with an A. So can you tell me, these are NBAs, these are input NBAs, what are the languages accepted by these automata? Still stupid question, so go ahead. Did I draw them too crappily or? Yes. Exactly. So exactly, they recognize one word, namely a to the omega. Okay, let's now do our product construction and move to the GNBA that is the product of A1. So this we use to denote the product of A1 and A2. Now, let me go back here. Maybe you can tell me, what should the product look like? What should I draw? Nothing? No? Too early? Yes? Exactly. So let's do Q1, R1, and this is an initial state, right? Our only initial state, and we have Q2, R2. And since the automata need to move synchronously, we have these transitions in there, right? Because both of them need to take a step at the very same time, so we can only have Q1, R1 and Q2, R2. Okay, now suppose for a moment we don't do this, you know, let's say complicated acceptance condition, but we do the regular acceptance condition for the product construction on NFA. Which of the two states would be accepting? Answer is none, right? Because in none of these two states are both automata in their accepting state. But, you know, then this would mean that the language is empty, right? Because this is supposed to be, so if we interpret it as an NBA, the language is empty, right? Okay, so this doesn't work. So we need to, this is why we need to have this criterion that's a little bit more complicated. So what we have to do is we take A3 as a GNBA, and its acceptance condition is the following. This is curly F. So we now need to spell out this acceptance condition for this example, meaning that we have in the first component all states that are an accepting component in their first element here. So what states are this? It's Q1 R1 and it's Q1 R2. I mean, I didn't draw the remaining states. There are two more states. They are just not reachable from the initial state. Okay, so I omitted them here, but technically there are two more states in this product. Okay, this is one set of accepting states. This, let's call it F1. And the second one is the dual, namely we have Q1 R2 and Q2 R2. We call this F2. Why are these accepting in the second acceptance set? Well, because their second component, namely the R2, is an accepting state of our automaton A2. So if we put it like this, then we're exactly having our acceptance condition as we defined it for the product GNBA. Okay, but now we're not happy with our GNBA. We want an NBA, so let's apply the reduction from GNBA to NBA that we've seen before. So we do basically A3, GNBA to an NBA A4. And the NBA would look as follows. So we start in the initial state of the GNBA, namely Q1 R1, and in the first component. Okay, this is our initial state. Okay, where can we go from here? First of all, we observe Q1 is accepting in the first automaton, right? So with respect, I should say with respect, no. This state, Q1 R1, is accepting in F1. This is why in our first copy, this is an accepting state. And it means that we change the outgoing transitions to move to the second component, to the second copy that we need for F2. So we move to Q2 R2, but this time in the second component. And now Q2 R2 is an element in F2, meaning that we change the outgoing transitions to enter the first component again, because we only have two sets of accepting states, F1 and F2. And that's also labeled with an A. And if we now look at this one, then we see, it still recognizes the word A to the omega. So we have L omega of the NBA A4 is exactly L omega of the GNBA A3, which is the set containing of one infinite word, namely A to the omega, which is also the intersection of A1, of the language recognized by A1, intersected with the language recognized by A2. Okay, so what have we done? We have taken two NBA, we have constructed the product GNBA, and we've reduced the GNBA to an NBA again, and we've seen, yes, in our example it works, and you can also prove that it works in the remaining cases, that this construction tells you omega regular languages are closed under intersection, because we can find non-deterministic Büchi automata that recognize the intersection languages. Is that clear? I hope. Okay, and let's come to the summary of today, and probably close a bit early today. So what have we learned about omega regular languages in this long lecture, and not only this one, but also the last one? You've seen that omega regular languages agree with several classes of languages. First and foremost, they coincide with the languages that you can specify by means of omega regular expressions. Professor Gatun has shown this to you. Secondly, they also coincide with the class of languages for which you can find an NBA that recognizes this language. So NBA and omega regular languages have the same expressivity. And as you've seen in this lecture, even if you allow for more accepting sets of, accepting states that all need to be visited infinitely often, you don't gain expressivity, but you can reduce it to a non-deterministic Büchi automata again. So you also have that GNBA recognize exactly omega regular languages. But as I've shown you, deterministic Büchi automata are strictly less expressive. There are omega regular languages that are not DBA recognizable. There is no DBA that recognizes this language. And finally, we have seen, at least in parts, that omega regular languages that are recognized by NBA and GNBA are closed under all important operations, union, intersection, and complementation, out of which union is clear again from the fact that you have omega regular expressions characterizing the same set of languages, and you have a plus in these omega regular expressions. Intersection, we have seen the GNBA construction for this, and complementation, we didn't deal with that because that's pretty much complicated, and you might see that in another lecture. Not from us, but if you're interested in that, I would advise you to visit Christoph Lüding's very, very good lectures on this. Well, and if there are no questions, then we're done for today.